Have you ever wondered what would happen if three planets were placed side by side in space? How would they move? Would their paths be predictable? The three-body problem unveils one of the greatest mysteries in physics. Why is it so difficult to predict the motion of three objects in space? The three-body problem is a classic puzzle in celestial mechanics that highlights the difficulty of predicting the movement of three massive objects, such as planets or stars, when influenced by their mutual gravitational forces. While the motion of two bodies, like the Earth and the Sun, can be precisely described by Newton's laws, the addition of a third body introduces a level of complexity that defies an exact solution. Historically, this problem has captivated the minds of some of the greatest mathematicians and physicists. Sir Isaac Newton laid the groundwork for understanding gravity and the motion of celestial bodies with his laws of motion and universal gravitation. However, when trying to apply these laws to three bodies, even Newton struggled to find a general solution. Later, mathematicians like Euler and Lagrange offered significant contributions by finding specific cases where the problem could be solved, but a universal solution remained elusive. At its core, the three-body problem shows that when three massive objects are interacting, their gravitational pulls constantly change the motion of one another. This creates a system where the orbits or trajectories are chaotic and incredibly difficult to predict, even though the underlying physical laws are well understood. Key points. Definition of the three-body problem. Historical background: Newton, Euler, and Lagrange. Why the problem is mathematically complex: the unpredictability of multiple interactions. This sets the stage for a deeper exploration into why the three-body problem has been a challenge for scientists for centuries and how it continues to puzzle physicists today. The three-body problem stands out as one of the most complex and fascinating challenges in celestial mechanics. While the motion of two bodies interacting through gravity, like the Earth and the Moon, can be neatly predicted using Newton's laws, the introduction of a third body turns this orderly system into a chaotic dance of gravitational forces. In a two-body system, the gravitational pull is direct and calculable, resulting in predictable orbits. But with three bodies, each one exerts an ever-changing influence on the others, creating a dynamic system where the gravitational forces are in constant flux. The trajectories of these bodies no longer follow simple, repeatable patterns. Instead, they can shift dramatically in response to even the smallest changes in their initial conditions. This is the essence of chaos theory. Chaos theory explains why, in a three-body system, the tiniest variations in starting positions, velocities, or angles can lead to wildly different outcomes over time. Imagine two planets and a moon orbiting one another. If one planet is nudged just slightly in any direction, the entire system might evolve into a completely different arrangement. The gravitational pull between the three bodies creates a web of interactions that quickly spirals into unpredictability, making it nearly impossible to forecast their precise movements over long periods. This sensitivity to initial conditions, known as the butterfly effect, is what makes the three-body problem so captivating and frustrating for physicists. Despite understanding the underlying forces at play, the chaotic nature of the system means that small uncertainties grow exponentially over time. In practice, this means that no matter how accurate the initial measurements are, long-term predictions become unreliable, and the motion of the bodies can only be approximated for a short duration before diverging into uncertainty. The three-body problem isn't just a mathematical curiosity, it reveals the inherent unpredictability of nature itself. Even in a universe governed by laws that seem deterministic, chaos emerges when systems become sufficiently complex. This problem serves as a powerful reminder of the limits of human knowledge and the mysteries that still lie within the cosmos. Despite the inherent chaos of the three-body problem, scientists have not given up on trying to understand and predict the behavior of such systems. While a general, exact solution to the problem remains out of reach, numerous approximate solutions have been developed over the centuries. These approaches allow us to gain insight into specific cases or make short-term predictions, offering valuable tools in fields ranging from astrophysics to space exploration. One of the earliest breakthroughs came from the work of mathematicians like Joseph Louis Lagrange and Henri Poincaré, who discovered special cases where the three-body problem could be solved under very specific conditions. Lagrange identified a set of points, now known as Lagrange points, where the gravitational forces between the three bodies balance out perfectly, allowing an object placed at one of these points to remain in a stable position relative to the others. These Lagrange points have practical applications today, such as in the positioning of satellites, which can orbit in these stable regions with minimal fuel usage. Poincaré's work was even more profound, as he proved that, in general, the three-body problem has no exact, closed-form solution. His insights laid the groundwork for the field of chaos theory, helping scientists understand that some systems, while governed by simple laws, are inherently unpredictable. However, this unpredictability didn't stop the search for approximate solutions through computational methods. In the modern era, the rise of powerful computers has revolutionized our ability to tackle the three-body problem. Today, scientists use numerical simulations to model the interactions between multiple celestial bodies. These simulations don't offer an exact solution but instead compute the positions and velocities of the bodies step by step, over very small time intervals. By iterating through these tiny steps, we can get a reasonably accurate picture of how a three-body system will behave, at least over a limited period. This technique has been crucial for predicting the motion of complex systems, such as the interaction between the Earth, Moon, and Sun, or the orbits of planets in multi-star systems. It's also a vital tool for planning space missions. For example, when launching a spacecraft to a distant planet, scientists must carefully calculate the craft's trajectory to account for the gravitational influence of multiple bodies, ensuring it reaches its destination with minimal energy consumption. Without the ability to approximate the effects of the three-body problem, such missions would be nearly impossible. However, it's important to note that these numerical methods are not perfect. Even with advanced simulations, the chaotic nature of the system means that small errors or uncertainties in the initial conditions can still lead to large deviations over time. This limitation becomes especially significant when we attempt to predict the behavior of a three-body system over long timescales. Yet, despite this, numerical simulations have vastly expanded our ability to model and understand systems that were once beyond our reach. In addition to numerical methods, researchers have uncovered periodic solutions, which describe rare cases where the three bodies move in repeating orbits. These solutions are fascinating, as they reveal that, under certain conditions, even a chaotic system like the three-body problem can exhibit regular, predictable behavior. While these periodic orbits are exceptions rather than the rule, their discovery provides valuable insight into how complex systems can occasionally find a strange harmony amidst the chaos. The pursuit of solutions to the three-body problem has been both a challenge and a source of inspiration for scientists. It has pushed the boundaries of mathematics, physics, and computational science, leading to breakthroughs that extend far beyond the problem itself. As we continue to explore the universe, understanding the dynamics of multi-body systems remains a key to unlocking the mysteries of planetary formation, orbital mechanics, and even the future of space travel. The three-body problem, with all its unpredictability and complexity, continues to be a gateway to deeper exploration. Whether through approximate solutions, numerical simulations, or rare periodic patterns, it reminds us that even in the most chaotic of systems, there is still a wealth of order waiting to be discovered. The three-body problem isn't just a theoretical puzzle, it has significant implications in modern astrophysics. One key application is in the study of triple star systems, where three stars orbit one another in a complex gravitational dance. These systems are often unstable in the long run, with one star eventually being ejected or colliding with another. Understanding these dynamics helps astronomers predict the long-term behavior of such systems and offers insights into the life cycles of stars. Additionally, the three-body problem is crucial for understanding the formation of planetary systems. Early in the formation of a solar system, countless bodies interact, with many being ejected or colliding due to chaotic gravitational forces. This dynamic process determines which planets settle into stable orbits and which are flung into deep space. Understanding these interactions provides clues to how our own solar system formed and why some exoplanetary systems exhibit such diverse and unpredictable configurations. Moreover, the problem plays a role in gravitational assist maneuvers in space missions, where spacecraft use the gravity of planets and moons to gain speed and adjust their trajectory. Without an understanding of multi-body gravitational interactions, such precise navigation would be impossible. Thus, while the three-body problem remains unsolved in a general sense, its principles guide real-world applications, deepening our grasp of the universe's complex gravitational networks. For over 3 centuries, the three-body problem has challenged scientists, pushing the limits of mathematics and physics. While an exact solution remains elusive, the problem has paved the way for key discoveries in chaos theory and dynamic systems. It highlights a fundamental truth about our universe: even when governed by clear laws, nature can behave in unpredictable ways. The introduction of modern physics, particularly Einstein's theory of relativity and quantum mechanics, has added new layers of complexity to the problem. These theories offer fresh perspectives on gravitational interactions, especially when dealing with extreme environments like black holes or neutron stars. Yet, even with these advancements, the core unpredictability of the three-body problem remains a reminder of the limits of human knowledge. This puzzle continues to inspire researchers as it holds potential answers to broader cosmic mysteries, from planetary formation to the motion of galaxies. As we deepen our exploration of space, the three-body problem serves as a metaphor for our quest to understand the unpredictable, ever-changing universe. The three-body problem may remain unsolved, but it reminds us of the beauty and complexity and the power of curiosity. As we venture further into space, let it inspire you to keep questioning, exploring, and embracing the unknown. Share this journey of discovery with others, and let's continue unraveling the mysteries of the cosmos together.